This video covers Part 2 of Section 3.1, Proving Universal Statements. In this video, we're going to discuss proof by arbitrary element. Proof by exhaustion can, in theory, be used whenever the domain of the variable in the propositional function is finite. The method is only practical, however, when the domain is relatively small, although computers can be used to examine all the elements in a relatively large domain for certain types of statements. The method that we use to prove universal statements when proof by exhaustion is not feasible is called proof by arbitrary element. The idea behind a proof by arbitrary element of a universal statement for all x p of x is the following. We suppose that x represents a particular but arbitrary element of the domain D, and then prove that p of x is true for this element x. We can then conclude that p of x must be true for all elements in the domain D, and hence for all x p of x is true. This method of proof is also called generalizing from the generic particular. We are supposing that x represents an arbitrary or generic element from the domain, so x is a representative or a stand-in for the elements in the domain. We then show that the propositional function is true using an argument that applies or can be generalized to all elements of the domain D. Here's the procedure. To prove a universal statement of the form for all x in D, p of x, our first step is to suppose x is an arbitrary element of the domain D. This lets the reader know what the variable x represents in the proof. Since x represents an arbitrary element of the domain, we cannot choose a specific value for x. Proofs may involve several different variables, some arbitrary and some related to previously introduced variables. Whenever a new variable is introduced during the writing of a proof, it's important to specify what the variable represents. Second step, show that p of x is true for the arbitrary element x. So we need to construct a logically valid argument showing that the propositional function p of x must be true using definitions, axioms, previously proved results, and the laws of logic. Since x is assumed to be an arbitrary or generic element of the domain, we can only use properties which are common to all elements of the domain. We cannot make any assumptions about x that are not true for all elements in the domain D. The reason for this is that when we show that p of x is true, we need to construct a proof that will apply to all elements in the domain, not to just some of the elements in the domain. So for instance, if the domain D is a set of all real numbers, we cannot construct a proof that p of x is true that applies only when x is positive. Or if the domain D is a set of all integers, we cannot construct a proof that p of x is true that applies only when x is even. Before we can get started proving results, we need to have some basic definitions available to us. We'll start with the definition of a function. So for our definition, let a and b be sets. A function f from a into b is a rule or correspondence which associates with each element a in a unique element b in b. The set A is called the domain, and the set B is called the codomain of the function. And we denote the function with the notation shown, so f and then a colon and then a arrow b. The element b in b associated with an element a in a is denoted by our usual notation f of a, and we write b is equal to f of a. The element b equals f of a is called the image of a under f. The range of f is the set of all images under f. Note that some texts use the term range in place of where we're using codomain, and they use the phrase or the term image in place of range. We can represent a function f from a to b by a diagram as follows. So the domain A and the codomain B are each represented by an oval, so these are our two sets. The function f then maps an element a in A into an element b equals f of a in B, and the element b is the image of the element a. The range is a set of all images and is represented by the shaded oval inside B. We can now define properties of functions and determine whether or not specific functions satisfy these properties. So we'll start with the definition of an even function and an odd function. A real-valued function f from a into r is even, provided that for all x in a, our domain, f of minus x is equal to f of x. A function f from a to r is odd, provided that for all x in a, f of minus x is equal to minus f of x. And now for an example, let f from r to r be defined by the formula f of x equals x squared divided by x squared plus 1 for each x in r. We want to show that f is even. To show that f is even, we need to show for all x in r, f of minus x is equal to f of x. Since this is a universal statement with an infinite domain, then we use a proof by arbitrary element. Suppose x is an arbitrary real number, we need to show f of minus x is equal to f of x. To prove an equality like this, we usually start with one side, either the left or right, and we show it must be equal to the other side. So starting with the left side, this is f of minus x is minus x quantity squared over minus x quantity squared plus 1. And that follows immediately from the definition of our function f by replacing x with minus x in the formula. Now some algebra. Minus x quantity squared is just x squared. So this reduces to x squared over x squared plus 1. And according to the definition of our function, this is just f of x. So this equals the right side. Therefore, f of minus x is equal to f of x. And since x was assumed to be an arbitrary real number, this proves the universal statement for all x in r, f of minus x equals f of x. And thus f is an even function. For another example, let f from r to r be defined by the formula f of x is x plus 3x cubed quantity times e to the x squared for each x in r. We want to show that this function f is odd. To show that f is an odd function, we need to show for all x in r, f of minus x equals minus f of x. So we'll use a proof by arbitrary element again. Suppose x is an arbitrary real number. We need to show f of minus x equals minus f of x. The left side is f of minus x is negative x plus 3 times minus x cubed quantity times e to the minus x squared. And that follows from the definition of the function by replacing x by minus x in the formula. Some algebra gives us this is minus x minus 3x cubed quantity times e to the x squared. So minus x quantity cubed is just minus x cubed, and minus x quantity squared is just x squared. And now we have a common factor of minus 1 in the two terms in the brackets, which we can pull out, and this becomes minus the quantity x plus 3x cubed times e to the x squared. And we recognize that this is going to be minus f of x, again from the formula for our function f. This equals the right side, and therefore f of minus x equals minus f of x. Since x was assumed to be an arbitrary real number, this proves our universal statement, and thus f is an odd function. Next, we want to talk about absolute maxima and minima. A real-valued function f from a to r has an absolute maximum at a point x equals c, provided that for all x in a, f of x is less than or equal to f of c. A function f from a to r has an absolute minimum at a point x equals c, provided that for all x in a, f of x is greater than or equal to f of c. The diagram illustrates a function with domain the interval a to b with an absolute maximum at the right endpoint x equal b and an absolute minimum at an interior point of the interval. An absolute maximum corresponds to the highest point of the graph over its domain, and an absolute minimum to the lowest point of the graph over its domain. For an example, let f from R to R be defined by f of x is 10 minus x squared for all x in R. We want to show, using just the definition, that f has an absolute maximum at x equals 0. So in particular, we don't want to use any concepts from calculus, and we don't want to look at the graph of the function. Now, if we were to look at the graph of the function, we recognize that this function, the function's graph, is a parabola that opens down, and it has a vertex at x equals 0, so it follows immediately from the graph that it has an absolute maximum at x equals 0. But we want to use just our algebraic definition to prove this. So to show that f has an absolute maximum at x equals 0, we need to show for all x in R, f of x is less than or equal to f of 0. So we're going to use a proof by arbitrary element. Suppose x is an arbitrary real number. We need to show f of x is less than or equal to f of 0. Since f of x is 10 minus x squared, and f of 0 is 10 minus 0 squared, which is 10, then we need to show 10 minus x squared is less than or equal to 10. Since x is a real number, then we know that its square is non-negative, so x squared is greater than or equal to 0. Multiplying both sides of this inequality by minus 1, we need to reverse the inequality, so we obtain minus x squared is less than or equal to 0. Adding 10 to both sides of this inequality, we obtain 10 minus x squared is less than or equal to 10. And we see this is identical to the inequality we needed to show. Therefore, f of x is less than or equal to 10, or f of 0. And since x was assumed to be an arbitrary real number, this proves the universal statement. And thus, f has an absolute maximum at x equals 0. Now in this preceding example, we needed to show f of x is less than or equal to f of 0. And this was equivalent to showing 10 minus x squared is less than or equal to 10. A common mistake is to start with this last inequality. Subtracting 10 from both sides gives minus x squared is less than or equal to 0. Then multiplying both sides of this inequality by minus 1, we obtain x squared greater than or equal to 0. And since x is a real number, then we know that x squared is greater than or equal to 0, so we can say this last inequality is true. The reason why this approach is incorrect is that we are starting with the conclusion, namely 10 minus x squared is less than or equal to 10, which is what we need to show, and we're deriving something we know is true, namely x squared is greater than or equal to 0. So we're going backwards in the proof. We're starting with the conclusion, and we're deriving something we know is true. We cannot start any proof by assuming the conclusion or something we need to show. We always want to write down the conclusion so we know what we need to show, but we need to be careful not to use the conclusion in the proof. We're going to finish the video by talking about directions for writing proofs. In your earlier mathematics courses, you may have written up proofs using a far more informal style. For instance, suppose you're asked to prove the function f from R to R, defined by f of x is x plus 3x cubed for each x in R is odd. In a pre-calculus or calculus course, simply writing out f of minus x is minus x plus 3 times minus x cubed is minus x minus 3x cubed equals minus f of x may have been considered sufficient. In this course, and in your upper division mathematics courses to follow, you are generally going to be expected to write your proofs using a more formal style, adhering to certain guidelines, so the work above will not be acceptable. Over the years, the rules of style have become fairly standard for writing proofs. In later courses, as you become more experienced in writing proofs, you may be able to omit one or more of the following rules. As you're starting out in this course, however, you should be sure to follow each one. So our first rule or guideline is to write the statement to be proved in symbolic form. The symbolic form of the statement will determine the method of proof to be attempted. As part of writing the statement in symbolic form, you'll need to identify the domain of each variable. Next, you want to clearly indicate the formal beginning of your proof. Textbooks and your mathematics instructors will typically write the word proof to indicate the formal beginning of the proof, so you should do so also. Our third rule or guideline is to specify variables. This means you should identify each variable used in the proof in the body of the proof. Each time you introduce a variable, you should state whether the variable is arbitrary or arises from applying a definition or theorem, and what kind of object it is. In introducing variables at the beginning of a proof, you will generally say something like, suppose m and n are arbitrary integers, or let x be an arbitrary real number. Later on in a proof, you may introduce a variable that arises from applying a definition. For instance, if you know that an integer n is even, then you can write n is equal to 2k. But when you do this, you must specify that k is an integer. In this case, k is not an arbitrary integer, but follows from the definition of n being even. So you would state something like, since n is even, then there exists an integer k such that n is equal to 2k. Our fourth rule or guideline is to indicate your reasoning. At each stage of a proof, where appropriate, you should clearly indicate what you're supposing and what you're trying to prove. You should provide reasons for the steps in your proof. When you reach the end of a proof, clearly state that you proved the desired conclusion. And our fifth rule or guideline is to use correct English sentences. So your proof should be written up using correct and complete English sentences. Of course, you will use mathematical symbols to denote sets, elements, functions, and other mathematical objects, but mathematical expressions should always read properly within the context of the sentence. You should not use logical symbols, such as the symbols for all, there exists, or implies, in place of, or as abbreviations for the English words in a sentence. Such symbols should only be used as part of a logical statement, which will generally appear in a display. Finally, you also should not make up your own mathematical symbols or shorthand. There's going to be many mathematical symbols already in your proofs, and so you have to use the standard ones.